Okay, off we go. So here's where we were last time. We were asking this question about how can we compute the volume under a graph, right? And so broad strokes, the big idea was to look at slices, to recognize that slices have a cross-sectional area that you can compute. That cross-sectional area is in fact just an integral, and so we end up with an integral of an integral, right? And thus the term iterated integral. Okay, and we did an example. You got to make sure to remember which variable is playing what role at which stage of the calculation. The most important version of this is that for the inside integral, the outside variable is a constant, and thus that, for example, is all constant. Okay, a bunch of other details we talked about previously. Okay, so let's see here. So pick it up from there, if I remember correctly. Question comes up, could I slice in the other direction? Right, you got a loaf of bread here. You could slice it like so, as we did, or you could slice it the other way. It's perfectly legal, right? And it still remains, the whole is the sum of the parts, right? This total volume is the total of a bunch of the slices that you would get if you went the other way. Perfectly reasonable. The pictures that you get when you slice it the other way, highly analogous. Different, geometrically different, right? But highly analogous. Worth your time to try to reproduce. Likewise, the argument here, totally analogous. Definitely different, but totally analogous. I think this is a really worthwhile exercise, and I want to encourage everybody to do this on your own. And of course, as always, if you get stuck, come and talk to me. I'm happy to help. But persuade yourself that this is what you get if you slice it in the other order. And so what we have then, this is what y'all are going to confirm for yourselves. This is what we did last time. And so what you have is that the two iterated integrals are the same because they both represent the same volume. Okay, so said differently, you can switch the order of the differentials. You can do this move right here, right? Just keep in mind when you switch the differentials, you also have to switch the bounds accordingly. Okay. All right. Just a quick heads up, and of course, for the moment, we're only dealing with rectangles, but we will not always only be dealing with rectangles. We will very soon be looking at non-rectangular domains, and this result is only for the rectangular case. So when we get to non-rectangular domains, this little thing about the switcheroo of the, no, not the same anymore. This is only for rectangles. Okay, all right, now let's go back to what we were first looking at, and I'm going to say this is kind of analogous to the motivating example that led to integrals in the first place. Right, when the very first question that gets asked that leads us to write down single variable integrals is area under the graph curve. This is volume under the graph's surface, right? One dimension up from the motivating example for single variable integrals. So, okay, we got an answer. That, I mean, it's different, of course, but still, it's, we kind of see how it connects. We see the relationship. What else did we do with single variable integrals? Bazillions of things, right? We used single variable integrals to compute mass and work and population and you name it, loads and loads of things, right? By taking whatever it is that you're interested in, and I like the one-dimensional distribution of mass. They call it the mass of a rod example, right? So you have some weird metal rod of non-constant density, right, where maybe it's more dense over here and less dense over here, and how would you compute the total mass of that thing, right? The exact same integral construction, exactly what we needed to be able to answer that question. Sweet. I wonder if we would get so lucky here. After all, we've used the same motivating example, the analogous anyway, motivating example to compute, to motivate iterated integrals in the first place. What if I were to ask, an analogous question about mass. So this time, instead of a mass of a rod, where density is mass per unit length, let's instead ask, okay, what if I have mass distributed across a two-dimensional rectangular sheet? Right? And so it's not a rod, now it's a sheet of metal instead of a rod of metal. And now density is mass per unit area. Oh, well, again, it kind of feels like, can't we just write down the exact same thing? After all, it worked out for single variable calculus. Surely it should work out for us. Y'all can probably tell by my tone it's not going to work out. Well, here's what worked for the volume question. Here's what we, fingers crossed, are hoping will work for the mass question. And sorry to report, there's a nasty, nasty problem with this argument. It doesn't work. It really, really doesn't work. Here's where the problem's going to come up. If you look at this right here, in our volume example, where everything worked out nicely, it's because that right there was a height times a length, and that was two things. It was familiar, right? Height times length is area. We got lucky. The original question didn't have anything to do with area. It just happened to be that this we ran across something that happened to be familiar. Super lucky, right? The other thing is this super lucky break that we got encountering area. It's not just that it's familiar, it's an accumulating quantity. I can draw pictures like this, and I can argue that if you are interested in that area, then you can cut it into pieces like that, and I can argue that the whole is the sum of the parts, and this is what I like to call an accumulating quantity. The whole is the sum of the parts. And area is an accumulating quantity, and I know it is because I'm familiar with area. I understand area. It's perfectly obvious that area has this feature. Okay, all right, so back to the new question. And let's make the analogous, look at the analogous part of the story. That is, and let's remind ourselves, this density here, that's mass per unit area, because the mass is distributed across area. What do I get when I multiply mass per unit area times dx, which is a length? It's a swing and a miss. I don't know what that is. That's weird. Mass per unit area, I would get it if it was mass per unit area times area, but it's not. Right? So we lose. Yeah.
Could we not rewrite the length in terms of, could we not rewrite the length as area over height?
And there's various different ways that if you really wanted to cram this in and force it and make it work, it can be done, right? But two things. First of all, that's a tremendous amount of effort to go to, and it turns out there's a really easy workaround that is going to be far more desirable than that. So that's one thing. The other thing is if you do really push to make sense out of this, to understand what that is, which right this second we don't, and if you were to persuade yourself that that is furthermore an accumulating quantity, which again, really not obvious, right? Then what you would have is an answer to this one question of how to compute mass. And then when another question comes up and you want to compute population, okay, well, we're dead in the water again, and you're going to have yet another hard problem to have to deal with. So yes, it can be done, and this is not an efficient strategy, as it turns out. Does that make sense? Okay, so this is a nasty problem. And it's bad news, and we weren't expecting it, and okay, so we're going to have to figure out a more natural way around this. Ultimately, we come back to the very beginning here. Again, our motivating question. Volume under the graph, we were asking the wrong question. You think back to single variable calculus, and the very first question that we asked in single variable calculus when it came to integrals, what's the area under the graph? Not a very relevant question in most cases. right? Most of the time, ultimately not really what defines an integral, especially for applications. This is very commonly misunderstood. Most applications just don't have that much to do with area under a curve. So here's what we really should be thinking in terms of. We should be thinking in terms of generalizing not our favorite crutch example of a single variable integral. We should be thinking in terms of generalizing the definition of an integral. I missed. I cut off the... There we go. If you look at how an integral is defined as a Riemann sum. Now, commonly misunderstood. A lot of students think that this is some sort of outdated, who needs it? We've got the fundamental theorem of calculus. Huge mistake. That's not what this is. A lot of people think that this is nothing more than mathematical formalities that makes mathematicians happy. And no, to be fair, it is mathematical formality that makes mathematicians happy. And there's all sorts of beautiful math that goes into this and related ideas. But it is definitely not only that. There is a tremendously important, just to applications, right? Now, y'all are largely engineers. I'm not going to try to sell you on the idea that you should be super interested in mathematical formalities. As engineers, rubber meets the road. Solving problems, getting answers, building bridges, right? You need to understand Riemann sums. And let me try to persuade why. And that comes from this diagram right here. Let's think about all these applications that you got to be concerned about. And just for fun, let's pick one. I like mass. It's relatable, right? It's kind of visceral. Okay, how am I going to compute mass? And I'll tell you what they told me in high school, which I'd never understood, and that made me feel bad about myself. And then I realized, no, they're wrong, not me. Right? They just claimed that mass, of course, is equal to area. What? Right? Where did that come from? Oh, you want to compute the amount of mass on a, collected on an interval, maybe the mass of a rod? Well, so let's compute the area, they say. And I'm like, what? How do you? What? I don't. What? How do you get area out of mass? These are completely different things. It does not follow at all, right? And again, keep in mind, our goal here is not to get answers. Our goal is to make reasonable arguments that actually make sense. I don't think that's a reasonable argument that makes sense. To just assert that these two totally different quantities must be the same. Now, here's what was underneath, right? What they actually kind of meant by that was, well, if you take the mass and you chop it, and then if you represent the density as a height, and effectively, they're kind of flirting with making a Riemann sum that, yes, you can argue it could be interpreted as an area. But the point is, the only way to make this line here, the only way to make this argument make sense is ultimately, if the more reasonable and non-ambiguous you get, is to actually rewrite the mass as a Riemann sum, and then to observe that that Riemann sum also represents an area. So it remains this as an argument nonsense. All right, so now let's just think strategically. All right, if that arrow there is a bunch of nonsense, if we're going to have to make an argument about Riemann sums anyway, and look, if integrals have already been defined as Riemann sums, I don't need to jaunt downward to connect to area, only to then come back up to do the fundamental theorem. I don't need area at all. Let's just take our question and rewrite it as a Riemann sum, a.k.a. integral fundamental theorem of calculus, drop the pen and walk away. Area doesn't come up. Area is not needed. You can't connect to area anyway. There's no reason to be talking about area here. Does that make sense? Okay. So I think this is highly underappreciated. And again, the punchline here is that Riemann sums are the things that make it work. Riemann sums are what we can connect to from all of these applications. If you want to compute mass, break it up into a bunch of little pieces. add up all the little pieces you've broken it up into, namely, write it as a Riemann sum. Right? Riemann sums are the connection to applications. And this is, again, not mathematician formality, ivory tower abstractions at all. You take away Riemann sums, you can't make any of these connections, and you can't do any of these applications. Okay. All right. So if you want to hear more on that, I think I have a recording on it somewhere on my YouTube channel. But the punchline, this is what we need to be trying to generalize. If we want to make sense out of multivariable integrals, well, we need to take the definition of a single variable integral, namely a single index Riemann sum, and let's figure out how to sort of expand that to a two-dimensional setting. And that's what this is right here. All right, so reminder, if you have an interval, you're doing a single variable calculus problem, we chop it up into little pieces, like so. Various formulas you write down for x sub I and delta x and all of that stuff. You all have seen those formulas before. Right? A bunch of details that have to get put down. And then, big picture, we then say, having broken it up into pieces, let's look at one piece at a time. That piece, I can understand the problem as applies to only that one piece by saying, well, they told me mass per unit length. I'll just multiply that by length. No argument there. Mass per unit length times length gives you the amount of mass in that one little piece. And then we say, okay, fine, I'm going to add that up and take a limit for the round-off errors, blah, blah. We add it up and you get the total mass of the thing. Okay, so we're just going to do the same thing over here now. Why did I erase that? That was good. Okay. Suppose I have now a rectangle. Now, I'm not going to talk about volume. Don't care about volume. Right? You've already addressed the volume question anyway, and our interest here is in the Riemann sum formula as a, hopefully, fingers crossed, a computational strategy that will help us connect to applications. That's what I'm going to try to generalize and forget about volume. Okay, so let's slice it up. And let's see how well I can freehand these vertical slice. Oh, missed. That was terrible. There, I sliced it vertically. Notice that slices up the x-axis in what I'm going to call the usual way. These formulas I've got circled in purple there, I hope you recognize the exact same formulas that we wrote down from when we were doing single variable integrals. But I've got to slice it in the other direction too. Which slices up my interval from C to D on the y-axis. You get different formulas then. Analogous, but different. Right? And now I've got all the details documented. I've taken my rectangular domain, I've chopped it up into little pieces, and with all of those details done, let me now, one piece at a time, let's look at this little piece. Let's think through what do I know on this little piece. And again, I like the mass example. I find it very relatable. If I'm trying to compute the total amount of mass, okay, what about on this one piece? If I know mass per unit area, well, I've got formulas over here. I can just compute the area, and mass per unit area times area should give me mass. That's why we write down this right here. That's why we write down F times delta X times delta Y. The F has the ability, for example, just in the mass example that we're thinking about, this could be mass per unit area, which I then multiply by area. That gives me then in green here, I have the mass in that little piece, and then I add that up over all of the pieces, and that gives me the total mass. So this is what I'm going to call the one dimension higher analog of single variable integral Riemann sums that were so powerful that we saw back in the single variable calculus. Right? This was the thing that made the connection to applications. This is why we can compute stuff. Forget about area. Who cares about area? How often really is it that you've truly needed to compute the area of something? Very rare, right? Usually if you're doing engineering, you're worried about mass and work and force and torque and all sorts of physical quantities. Area is not usually one of them, right? The fact that this computes area, not the point. It's the fact that this computes everything else. That's the point. So likewise, this will also help us compute loads and loads of stuff. Everybody with me? All right. Okay, so this deserves a name and a notation. And here we go. All together, this thing is what we call a double integral. That's just a recopy. We're going to use this notation right here. I'm going to call that fairly natural in certain ways. The delta x, delta y, keep in mind the whole point of that was it represents a little piece of area. So how about dA as a shorthand in recognition that this represents a little piece of area. And now let's look at this summation business here. That summation, well, very importantly, we're adding up in two different directions. Now let's go back up to our picture here. We're not just adding just along the bottom strip here, right? We also have to add up vertically as well because we need all of these little pieces, right? If I'm computing the population of Wyoming, it's not good enough just to compute the population that's in this little strip down here. I need to go across the whole way, all the way up, which means I'm adding up in this direction and in that direction, and therefore adding up in two directions, and therefore pretty reasonable choice to use this symbol right here. I'm going to call this the double integral symbol. I want to encourage y'all to think of this as a single symbol. This looks like a single variable integral next to another single variable integral. That's importantly not what this is. This is a single thing that we draw as two integral symbols for kind of analogy purposes. Okay, is that cool? It's just notation. Okay. All right, so this is our new construction. We're going to do some really awesome things with this. Just a quick aside, it's on the content syllabus that y'all are not responsible for irregular partitions and test points, right? Y'all are absolved of all that stuff in the book. If you're interested, feel free to take a look. If you're even more interested and you want to see more about this kind of stuff, but I should point out, this is classic math. This is pure math. This is the analogy I like. This is the Mozart of classical math, right? This is beautiful, beautiful stuff. And Math 431, Math 531, great courses if you're into that sort of thing. Really, really good stuff. But for our purposes, we're only looking at continuous functions. When you're looking at continuous integrands, none of that makes any difference. And since we're mostly here for the answers, right, we're interested in computing stuff so we can build stuff. We're not going to worry about all of that irregular partitions business. Is that cool? All right. Okay, so let's do an example. Nice, convenient first example. We'll go back to our volume under a graph question. Right? Now, again, we've already done this. We already know that if you have a graph surface and sitting over some rectangular domain, you want to compute the volume sitting under that. Well, yeah, we did it. We did it with iterated integrals. We already know the answer. I just want to point out you could do it a different way now that we have this new tool. And that different way is to point out that if I look at one little piece of volume, I look at just the volume sitting over this little teeny tiny little sub-rectangular footprint. Well, that volume is height times the area of the base. And keep in mind that the height here is z, which is f of xy, which is that. And let's see, the area of my rectangular base, well, that little rectangular base, well, yeah, that's delta x, delta y, like we talked about previously. There's the width times length. And so, oh, yeah.
How do we, actually solve this?
Yeah. Coming.
Oh.
Coming. Yeah. Great question. A natural question. We'll totally get to it. For the moment, I just want to point out that this fits the form of the double integral, right? And so, and we're basically there because you can notice now that this is, in fact, exactly the definition of a double integral. So, sure enough, we can solve this problem with a double integral. Okay. Now, to your point, let's put the pieces together. We just got through computing this volume with a double integral. I previously confessed that we had already computed that volume with iterated integrals. Now, here's just the reality. If you answer the same question two different ways, you get the same answer. That means that because we're computing the same volume, these two things will always have the same values. So this is a super powerful observation, and I'll explain why it's so powerful in just a minute. But if you ever find yourself with a double integral and you need to compute it, the way you compute it is you recognize that it is take your pick, your favorite iterated integral, and you compute the iterated integral, which we already know how to do. Inside out, fundamental theorem of calculus. Is that cool? All right. So who cares? A very reasonable question. Okay, great. So we have a strategy for computing something I never cared about in the first place, right? So what's the win? Why am I wasting y'all's time on this? And this is the answer. There's a lot to say here. It's a complicated story. This was the very first thing we did. We wanted to compute a volume. We did so with iterated integrals. You can plug and chug with the fundamental theorem to get an answer. Old news. Okay. Let me remind you, though, what we've already observed. I made the observation that, you can't just claim mass is an iterated integral. We tried to make sense out of that. It didn't work. We found ourselves talking about mass per unit area times length. I don't know what that is. That's not a thing. You could make it a thing, but this is not a good, healthy strategy. Right? So we abandoned that. So don't try to make this argument. It just doesn't hold any water, right? If you claim mass, that's an iterated integral, just first cat out of the bag, iterated integral, it doesn't make any sense. Right? Okay. All right. Likewise, can you just immediately say mass is equal to volume? No. Again, totally different things. What are you talking about? You're making stuff up. That doesn't make sense at all. Right? So here's what we do. Here's why we care so much that we just showed that double integrals will always give the same value as iterated integrals. It's because that makes this three-step process viable. That's the point. Let me get rid of all the other stuff out of the way it's sort of confusing the picture. If I can argue, for example, that I can compute mass as mass per unit area times area added up over some region, just, this abstract double integral construction. Totally reasonable. Mass per unit area times area, mass. The units fit, everything works. That's what mass per unit area is for. It's to multiply by area to get mass. This is what it means. Right? And then I can say, I'm going to turn that double integral into an iterated integral. Thank you, theorem that we just argued, and then I'm going to compute that iterated integral with the fundamental theorem, and you got yourself an answer, and you can proceed with your practical application of whatever it is you need to do. We've computed the answer to an application question. Again, little zigzaggy sort of connect the dots process, but we've got an answer now. Is everybody on board? Okay. All right. Now I emphasize all three steps here are necessary. And again, I remind you, we're not interested just in answers. We're interested in reasonable mathematical arguments. And again, if you just do this, then you're making an argument that doesn't hold any water. It just doesn't, right? All you've got to do is just do this instead. Right? You're still going to get to that same iterated integral that you are still going to compute with the fundamental theorem to get the same answer. Yes, I know. But you don't have to write down nonsense. And the cost of this is at the low, low price of only simply having to recognize that mass is computed by a double integral, which you then instantly rewrite as an iterated integral. Right? So this is not a huge imposition. But from a conceptual standpoint, from a reasoning standpoint, it's immensely important. Let's see this in action. Here's that example that we failed at previously. Crashed and burned. Right? The pieces didn't fit. We were out of luck. Nothing that we can do. In particular, we're computing mass on a rectangular sheet where we're given mass per unit area. All right. Now I've stretched this argument out as fully as I think is sort of reasonably appropriate in this circumstance, just to be explicit, just to make the arguments as clear as possible. You don't normally have to write as much as what I've written here, and I'll talk about how you will actually write your solutions in a couple minutes. But let me go through the nitty-gritty details first, just to make sure that we're all clear. Okay. First. Mass is an accumulating quantity. The whole is the sum of the parts. I feel like this is a good thing let's recognize that is important in the argument. If you take a whole and break it up into little parts with the intention of adding up a sum of those little parts, you better know that the whole actually is the sum of the parts before you set that as the foundation for your whole argument. Right? So mass does have this feature. Lots of things have this feature. This is not a rare feature for quantities to have. Very importantly, not everything has this property. An easy counterexample. You see this rectangle right here? What if I were interested in the perimeter? Rhetorical question. If I were to compute the perimeters of all of the little parts, right? Add up these four lengths. If I were to compute the perimeters of if I were to add up all of those perimeters, would that give me the perimeter of the whole? No, it'd give me way too much. Right? So not everything is an accumulating quantity. And it's going to we're going to see some examples later on in the course where this concept of an accumulating quantity is a really important concept. It's going to figure very prominently in some arguments that we're going to make when we get to chapters 6 and 7. Okay. So anyway, this mass, indeed, the whole is the sum of the parts. On any given little piece, mass is mass per unit area times area. That's mass per unit area's job, right? The whole concept of having a mass per unit area is that it is something you multiply by area to get mass. That's what we mean by per, right? Everybody happy with that? Let's see, and then, check it out. That's exactly a Riemann sum. That's the very definition of this double integral. Okay, so I have successfully turned mass into a double integral, and coming back up to where I was up here, let me clean up the mess. What I've got there is this first step of the problem. All right, next. We're basically done at this point. Next, I've got to just rewrite the double integral as an iterated integral. Cool. That's straight out of the theorem. The theorem says double integrals give the same value as iterated integrals. Sweet. And then lastly, plug and chug, fundamental theorem. Yeah. And okay, so I'm going to leave that for y'all to crank out those details. Well, if we had all the necessary specifics. So that's the 3-step process. This is kind of what I expect y'all to do on the exam, but with the following streamlining. You don't really have to write all of that stuff. Again, I just put that in there just as I wanted to make sure you were clear how I got to this first step. But if you say mass equals double integrals equals iterated integrals, and then if you plug and chug with the fundamental theorem to get an answer, totally fine. All good. The key point, I need to see the double integral. That's the recognition that application to iterated integral doesn't hold any water. That doesn't make sense. That just doesn't make sense, right? So give me the double integral, right? To make it clear that that's not what you're doing, you write down the iterated integral, you plug and chug. Everybody clear on what I want to see? Right? Look at the low price here. The only difference between a full credit solution and a real problem, the only cost is you got to write down that right there. That's it. Just write it down. It's so little, right? Yeah.
Slightly related.
Yeah.
But if we were given, say, a triple integral, could we just extrapolate that to?
You're way ahead of things. That said, I did interrupt. I'm sorry. Go ahead.
I mean, could we extrapolate to like a 3 integrated integrals? Or an integrated integral with 3?
Okay, so your question's what I thought it was. Yeah, you're way ahead of me. Yeah, all right. It's a very natural next thought, and yes, we will spend a bunch of time talking about that. Probably, we might start that on Friday, but certainly very soon. Yeah, right. Yep. Yes.
You crossed something out and said not to write that.
Yeah.
What was it?
Yeah. Don't just go straight from here to here.
Okay.
Right, because then you're making that, again, that's that argument that I claim just doesn't make any sense. And it's not that it gives you a wrong answer. It'll get you to the same iterated integral. But it's not about the answer, it's about the reasoning. And yeah, right. I know I say it too much. Yeah.
No.
All right. Okay, one other thing I want to say about notation. People notice that you do enough of these kinds of questions, you just start to notice certain patterns, and this limit summation eventually gets replaced with a double integral symbol. And so, in fact, even though we technically haven't made sense out of this expression, double integral dm, where's the definition of that? There's no definition of that. Hasn't been written down, right? But as a shorthand, with the understanding that this just is kind of a math slang for that, right? People do this all the time. It's perfectly reasonable. It's a little sloppy. It's forgivable because it's very convenient. Likewise, eventually you notice that the deltas turn into D's. So why not just go ahead and start off with that? Again, it's a little sloppy. There's no M axis, right? So it's a little fishy, I suppose. But again, very, very common mathematical shorthand, totally fine. I do it all the time. I encourage it. Right?
So that second row is like
perfectly fine. Yeah, if you were to write this, that's perfectly fine. And again, in fact, you can also just say that, and that's also perfectly fine. Yeah. Right. Is that cool?
I thought you just said you couldn't.
No, you can't do this.
Oh.
That would be bad, because that leaves out the important point that there is a double integral. This is the double integral right here that I want to make sure that you get.
Okay.
Yeah, right. But again, after you go down this road enough times, you're going to have seen enough examples where, hey, compute the mass distributed across an area, and yeah, double integral of density, it's fine. Yeah. Okay. Mostly just as an example of how this little shorthand is convenient, so I don't want to spend a lot of time on this example. If you want to read through the rest of the details of this example, it's totally fine. It's a cool example. It's an interesting little application. Where this came from, by the way, is many, many years ago when my house was being built, there was this facade on the front of the house that's built out of stone. It's basically a little sort of wall, but it's just one of these facade walls. I don't know if y'all seen that kind of thing. So it occurred to me as the guys were building the wall that that's a lot of stones that look heavy, and they had to pick them all up off the ground. Right? It just looks like a lot of work. And it occurred to me, hey, oh my gosh, how much work are they actually doing there? Right? Seems like a reasonable question. And by the way, yes, I do in my everyday home life try to figure out how to incorporate multivariable calculus, right? And there's various other examples. Quick preview, when we get to scalar line integrals that we'll talk about in chapter 6, one of the examples I'm going to show you is how to compute the amount of work that you perform when you shovel your driveway after a snowstorm. And that occurred to me because I shoveled my driveway after a snowstorm. And I wanted to be able to brag about how much I did. So here's the big idea. We've got this great big wall here, and we're going to be adding up the amounts of work associated to each individual piece. But for each individual piece, if I can compute how much work it is on each individual piece, the whole is the sum of the parts. And again, now I claim this is physically sort of, you just got to think about what is the nature of this stuff we call work. And the grand total is, it's the sum of all of the individual micro tasks. Okay? One brick at a time. Okie dokie. Now let's look at that one brick. On that one brick, I argue that work is force times distance. Now, one of the little peculiar particulars of this example, you'll notice I've given density here as some formula. I didn't give any units. My intention here was that this formula, I made this up, of course, right? But my intention is that this be not mass per unit area, but this is weight per unit area. And this is a common choice, however unfortunate, right? In the U.S., we don't talk about mass in terms of grams or kilograms. We talk about mass in terms of pounds, right? Pounds isn't mass. Pounds is force. And so y'all who have taken physics classes probably remember that you got to throw in an extra factor of g sometimes. You got to think through when to do that, and that's a whole little physics digression. And if anybody wants to talk about that, come talk to me. I'm perfectly happy to do it. But here, I'm just going to say we're sidestepping that problem by this being weight per unit area. And so weight, of course, is a force. And so work is force times distance. And that force is force per unit area times area. Weight per unit area times area. Is that cool? Oh, and I kind of skipped over a detail here. The distance, so looking at the green equation here, so I claim that work is equal to force times distance. The distance is y because that's how far you have to lift it up to get it to its position that it's going to go into on the wall. All right. So anyway, so the punchline to all of this, two punchlines. One is we've gotten this down to an integral. That's an iterated integral that you can punch up a bunch of algebra and arithmetic to healthy exercise. Go through and make sure you follow all those steps. Make sure you come up with the same answer I did. Right? I'm pretty sure I'm right at this point. I've been using these notes for several years now. No one's corrected me yet. I think it's right. But it's always possible that I've made a mistake, right? So if you do find an arithmetic mistake in my notes, please let me know, right? It's not impossible at all. The other upshot, and again, the reason I wanted to do this example is to point out how convenient it is to develop the Riemann sum using this integral shorthand. It's just a lot more streamlined than all of that you could rewrite as with summation notation and limit as n approaches infinity, blah, blah, blah. But it's just clunky notation, and this is just a lot easier to write down. Okay. All right. Okay, let's see here. We got 5 minutes. That's good. Okay. Okay. So the next question I want to ask, what if our domain is not a rectangle? And there's a lot to say about this. This is where stuff gets really interesting. This is where geometry starts to get challenging, and we're going to have to draw some pictures and think about, processes very carefully. Here's the good news. Practically everything works just exactly the same. There are formalities as to how we define double integrals. That's not what this course is about. Again, take Math 531 if you want to see a proper development of how to define a double integral carefully, right? But the punchline is it's exactly what you think it is. We're going to take this domain. We're going to chop it up into little pieces. Some of them won't be rectangles. That's okay, as it turns out. We're going to take this, chop it up into little pieces, and say the whole is the sum of the parts, and stuff per unit area times area gives you stuff, and it's all the same, right? It's exactly what you would think. Looking at the volume example, yes, the total volume is the sum of the volumes of the slices. Take a loaf of bread, slice it the other way. Still, the whole is the sum of the parts. Right? The volume of a slice of bread is area times thickness. Yeah, sure, of course. That area is still an integral. Cool. Everything works. Except for one little detail is different. And that is, you'll notice, let's think about this this inside integral where we have x going from a to b. Right? So that represents, x, as we go in that direction. Right? As we're, computing the integral to get this cross-sectional area. Notice where we start. We're going to start at that point because that's where the slice of bread starts. Right? The x-coordinate depends on y. And you just have to look at the picture. Think about what would happen if you take a different y. If you move that direction, well, then we'd be looking at a different range of values of x, and it would have a different starting point, which would give me a different x-coordinate for the lower bound. So that's the only thing that matters. The only thing that changes is that your inner integral is going to have bounds that are now functions instead of constants. And in particular, in the geometry of this picture, is how it always works out. Your inner bounds will always be functions of the outer variable.
That's always true.
Always true. Inner bounds are always functions of the outer variable. And here's the last thought that I'm going to drop on you, and then we'll worry about extra details next time. Let's think about this process about, how would I figure out what these two functions are, the a of y and the b of y, these inner bound functions. Well, you can see right here in the picture, it all, I wanted to switch colors there. It all happens in the xy plane. It's only about the shape of the domain. The shape of the domain is what determines where you start and where you end. All this third dimension stuff, the height, irrelevant. Right? I didn't make a reference to this point up here at all when I was talking about that lower bound. Right? The height doesn't matter. So, in fact, this three-dimensional picture, when it comes to thinking about those bounds, this three-dimensional picture is way more complicated than we actually need. All we need is a picture of the domain. And we've got to think about one value of y at a time, and then think about, well, where does my integral start? Where does it end? And then look at those x-coordinates. And so we're going to be looking at this picture, nice and two-dimensional. Much easier to draw And this will tell us everything that we need to know to figure out our bounds, and we'll pick up there next time. Y'all have a good rest of your Wednesday. See you Friday. Don't forget about attendance.